heat transfer. In this lecture, I will be explaining about the design problem of the double pipe heat exchanger, and this lecture is actually the continuation of the previous lecture that was the lecture number 6, part 1. So in this lecture, I will be explaining about the design of the double pipe heat exchanger. So based on all the 14 steps that we had studied in the previous lecture, let me just read the question statement or the problem statement, that we have a double pipe, we have to design a double pipe heat exchanger in which there are two fluids. The one is known as benzene and the second one is known as the toluene. So it is desired to heat 9,820 pound per hour of cold benzene from 80 to 120 degree Fahrenheit. So benzene is our cold fluid and it has a mass flow rate which is given over here, 9,820 pound per hour. And we have to heat this cold fluid from 80 to 120 degree Fahrenheit using a hot fluid which is a toluene in this design problem. And this hot fluid will ultimately be cooled down from 160 to 100 degree Fahrenheit. So some of the fluid properties are given, that the specific gravities at 68 degree Fahrenheit are, that is 0.88 and 0.87 respectively for these fluids. So the other fluid properties will be found in the appendix, and I will show you the tables as well as the diagrams from which I will take the fluid properties for these two fluids. So the fouling factor that we had studied in the previous lecture, it has a great importance in the design of the heat exchanger, which is given over here, that is 0.001 should be provided for each stream. So we have two streams, right? So one is in the inner pipe, one is on the outer pipe. Annulus region, so this fouling factor would be doubled, right? It would be 0.002. I will use this value in the upcoming slide. So the allowable pressure drop on each stream is 10 psi. So we have to design the double pipe heat exchanger and we have to show that whether the pressure is in this limit or not, right? So we have two streams, the one is the cold stream and one is the hot stream. So one is in the inner pipe and one is in the annulus region of the double pipe heat exchanger. So ultimately we have to calculate the pressure, so based on the given criteria, whether the pressure is in the allowable limit or not. So a number of 20 feet hairpins are given. So hairpin double pipe heat exchanger we have already studied about, with the configuration of 2 by 1 into 1 by 4 inch IPS pipe standards are available. So how many hairpins are required? So first of all, we'll have to design the double pipe heat exchanger. We'll have to show whether the pressure on each stream is in the allowable limit, and we have to calculate the total number of hairpins that we have to use in the design of this heat exchanger. So let's have a look on the design of this double pipe heat exchanger. So the first step of the design of the double pipe heat exchanger, that you have the 4 different temperatures, T1 and T2. Capital T1 and capital T2 are the inlet and the outlet temperature of the hot side, and the capital small T1 and small T2 are for the cold side temperatures, cold side or the cold fluid temperature. So first step is check the heat balance, and using the specific heat, the value of C that you have to calculate at the average temperature of the hot fluid and the average temperature of the cold fluid. You have to perform the heat balance, and ultimately whatever the parameter is missing, so you have to calculate that parameter. So this is the first step. So first of all, for the benzene, which is the cold fluid, right? So the average temperature is 100 degree Fahrenheit. So inlet is 80 and the outlet is 120. By taking the average, so we'll have the average temperature of the benzene, that is 100, right? And similarly for the toluene, the average temperature is 130. By taking the average, that is inlet of the toluene, that is the hot fluid, is 160 and the outlet is 100. Taking the average, we have 130. So the first step is from this 100 degree Fahrenheit, we have to put the values for the cold fluid, and we have to calculate the total amount of heat which is basically absorbed by the cold fluid, right? So this benzene is the cold fluid, right? And for this is the formula: Q is equal to W, that is the mass flow rate, C is the specific heat, right? And this is the temperature difference. So the mass flow rate is 9820 is given, and this is the specific heat, the value of C, that is 0.425 BTU per pound per degree Fahrenheit, multiplied by the temperature difference. So the overall heat that is basically absorbed by the cold fluid from the hot fluid, that is 167,000 BTU per hour, right? So the question is, from where you can get the value of C, the specific heat. I will explain it in the upcoming slide. So the amount of heat which is basically absorbed by the cold fluid is equal to the amount of the heat which is basically released by the hot fluid, right? So keeping in mind that there is no heat loss in the surrounding, so the heat exchanger is properly insulated, and there is no radiation heat transfer. So based on that, so we will say that the amount of heat which is basically absorbed by the cold fluid is equal to the amount of heat which is released by the hot fluid, right? So we have the heat, or the for the for the cold fluid that is basically absorbed, which is 167,000. Now we have to calculate the mass flow rate for the hot fluid, which was not given in the question statement. So we have the heat, right, and we have the specific heat, and we have the temperature difference. By rearranging this formula into this form, so we will have the mass flow rate for the hot fluid, which will be equal to 6,330 pound per hour. Again, the question is from where we can get the value of this specific heat. In the step 1, everything is given in the question statement except the values of the specific heat. Let me just show you the values of the specific heat in the upcoming slide. This is the slide that. So you can take the values of the specific heat from these average temperatures. Let me just show you how to calculate or how to get the value of the specific heat. For example, the average temperature of the benzene is 100 degree Fahrenheit. So this is the initial point, right, for the benzene, right? For the benzene. So 100 degree Fahrenheit. This is the average temperature, right? So these are the different points which are given for different liquid components. So this is the benzene, right? This is the benzene, and it has at number 23. So you have to locate the number of a circle which is here, that is 23. So this is your starting point, and this is the second point. So you have to draw the straight line from 100 degree Fahrenheit to 23, and then extend the same line up to this point, and you will meet, or you will reach at this point, which will be your specific heat for the benzene, right? So the specific heat of the benzene is 0.425. Similarly, for the toluene, which has the average temperature of 130 degree Fahrenheit. So this is 130 degree Fahrenheit for the toluene, which has again the value that is 23, which was given in the table number 6 and on the lower hand side. So again, toluene is at number 23. You have to draw the straight line from 130 degree Fahrenheit to 23 point, and then extend this point. So this value will become 0.44 BTU per pound per degree Fahrenheit. This is the specific heat of the toluene. So this is all about the first step, that you have to perform the heat balance and check the properties and to determine the unavailable parameters. For example, in this case, the heat is not given, the heat balance. You have to perform the heat balance, and you will get the amount of heat which is basically absorbed or evolved, and ultimately you will have to determine the mass flow rate for the hot fluid. So the second step is in the design of the double pipe heat exchanger is determine the log mean temperature difference, assuming the counter current flow. So you have to arrange your 4 temperatures in this form, like the hot fluid and the cold fluid, and the lower temperatures and as well as the higher temperature. For the cold fluid, the lower temperature is 80 degree Fahrenheit and the higher temperature is 120 degree. And for the hot fluid, the lower temperature is 100 and the higher temperature is 160. Taking the difference, so you will get the delta T1, that is the temperature difference between the hot and the cold fluids for the lower temperatures, and delta T2 is the temperature difference between the hot and the cold fluid, right? 160 minus 120, that will be 40. So this is again the delta T2 minus delta T1, right? 40 minus 20, that will be 20. So this is the formula, the famous formula for the log mean temperature difference, right? So usually you have seen that there is the natural log. When you convert the natural log into the simple log with the base 10, so you have to multiply it with 2.3 with the simple log with having the base 10. So after simplifying that, you will get the value of the log mean temperature difference, assuming the formula or assuming the flow of the 2 fluids in counter current or in opposite direction. So the next step is, after the LMTD, you have the third step, you have to calculate the caloric temperatures. So I have already explained this point in the last lecture. So there are some points that whether you should go for the caloric temperature, or you can just simply get the average or arithmetic means of the temperatures of 2 different streams, right? So caloric temperatures are checked for the both streams will show that the neither is viscous at the cold terminal and the viscosities are less than 1 centipoise. So it is given over here from this point to this point, right? You will see that if neither of the liquid is very viscous at the cold terminal, say its viscosity is not more than 1 centipoise, and this is the first point. If the temperature ranges do not exceed 50 to 100 degree Fahrenheit, this is the second point. And the third point is if the temperature difference is less than 50 degree Fahrenheit. So based on these 3 conditions, you have to take the arithmetic or the average temperatures of these 2 streams instead of calculating the caloric temperature. So you can determine the caloric temperature if no condition is basically in this case, and simply if none of the condition is is in this case, so you can determine the caloric temperature. But in this case, so we have seen that the viscosities are less than 1 centipoise and the temperature ranges are in moderate range, which means up to 50 degree Fahrenheit. So we can just assume one more thing, that the viscosity correction parameter also equal to 1. So instead of going for determining the caloric temperature, you can just take the average temperature of the cold fluid and the hot fluid. This is the average of the hot fluid and this is the average of the cold fluid. Now you have to go for the other parameters that go for the inner pipe. You have to go for the table number 6, and you have to check the flow areas for the inner pipe is greater than the annulus, which is given based on the pipe diameters in the question statement. So place the larger stream, that is benzene, in the inner pipe. So let me just show you the table 6.2. This is the table 6.2, and this is the configuration, which is 2 into, this is 2 inch the outer pipe diameter, and 1 into 1/4 is the inner pipe diameter. So if we see the flow area of the annulus region and the flow area of the inner pipe, so we can say that the inner pipe flow area is larger, right? So we have to see that which of the stream has the higher mass flow rate. So simply when we see that in this slide, so the benzene, which has a mass flow rate, is 9,820 and the toluene is only 6,330. So obviously benzene has the higher mass flow rate, so we can place benzene in the inner tube based on its higher flow area. So the fourth step is to determine the flow area, right? So the formula of the flow area is for the pipe, that is pi d square over 4, right? So the units will be in the feet square. So for the pipe, so in the inner pipe we have selected the benzene because of the inner pipe has the high flow area as well as the benzene has the high mass flow rate. So this is on the right hand side will be the calculations for the inner pipe, and the fluid which is flowing through the inner pipe is benzene, and from the left hand side we have the outer pipe or the annulus region, and which is the hot fluid, and the fluid name is the toluene. So the formula for the flow area, that is pi d square, right? So which is given over here. Now we have to calculate the diameter for the pipe. So the dimensions in the IPS standard, so this is given over here. So in the IPS standard for the inner pipe, that has a dimension given in the question statement 1 into 1 by 4, and we have to consider the inner pipe, and the inner pipe diameter is 1.380, right, which is taken from the table number 11, right? So 1.38, which is given in the inches, right, which is given in the inches. In order to convert this diameter for the inner pipe or the inner diameter of the inner pipe into feet, we have to divide it into 12. So we will get the value of the diameter of the inner pipe, inner diameter of the inner pipe, that is 1.115 feet. So after putting the value in this formula, which is given over here, pi d square over 4, so after simplifying that, we will have the flow area, that is 0.0104 feet square, which is the flow area of the inner pipe, right? And similarly, we have to calculate the flow area for the annulus region. Instead of putting simple d, we have to use this annulus region, right? And this diameter is actually the difference between the outer diameter of the inner pipe, right? And we have to take the inner diameter of the outer pipe. So keep in mind that I'm repeating this. So in order to calculate the annulus region flow area, you have to use, or you have to take the difference between this diameter at this point where my pointer is moving, right? This is the inner diameter of the outer pipe. This is the outer pipe which has the inner diameter, and the second diameter is, which is D1, which is the outer diameter of inner pipe. So the dimensions in the IPS standard given, that is 2. For the 2, we have to take the diameters for the annulus region, which is given over here. For the nominal pipe size IPS standard in the inches, which is given over here, the inner diameter is 2.067, right, for the outer pipe, and the inner diameter is only 1.66, right? So 1.66, what is 1.66? 1.66 is this outer diameter of the inner pipe, and 2.067 is the inner diameter of the outer pipe. So these diameters are given in the inches. We have to convert them into feet. After dividing the D1 and D2, we have to convert in feet. So these are the diameter, the D1 and the D2, in fits, and after putting the values in the flow area and after solving it, we will have the flow area for the annulus region, that is 0.00826 feet square, right? And also we have studied that for the annulus region and for the determination of the Reynolds number and other parameters, we have to calculate the equivalent diameter. So we have given with the D1 and D2, we can simply put the values over here in this formula for the equivalent diameter, and the value of the equivalent diameter is 0.0762 feet. So we will have to use this value in the upcoming slide for the determination of the Reynolds number and other parameters. So the fourth step is to determine the flow area of the inner pipe, that is on the right hand side for the cold fluid, and the cold fluid is benzene. And for the annulus region, which is the hot fluid, in the benzene is flowing in the annulus region, and this is all about the calculations for the determination of the flow area. So the next step is the fifth step, in which you have to calculate the mass velocity, that is GP. And the formula for the determination of the mass velocity is by using the mass flow rate divided by the flow area, right? You will have the mass velocity, which has the unit of pound per hour per feet square, right? So the next is the sixth step. I will explain it how to get the values for the sixth step, but the first step is the fifth step is to determine the mass velocity. So for the annulus region, you have the mass flow rate of the toluene, yes, which is given, which you have calculated in the first step, the mass flow rate 6,330, and in the previous slide you have just calculated the flow area for the annulus region. By dividing the mass flow rate with the flow area, you will get the mass velocity for the annulus region or for the toluene. And similarly for the inner pipe, in which the cold fluid is moving, and which is the benzene, and it has the mass flow rate which is 9,820, which is given in the question statement, and it is divided by the flow area, which you have calculated in the previous slide. And after dividing the mass flow rate with the flow area, you will get the mass velocity, which is 43,000 pound per hour per feet square. This is all about the fifth step. In the sixth step, you have to calculate the Reynolds number, right? For the Reynolds number, right? So you have to calculate the Reynolds number for the inner pipe separately, and you have to calculate the Reynolds number for the annulus region separately. For the Reynolds number, what you have to do is you have the values of the diameter. For the annulus region, you have to use the equivalent diameter that you have already calculated the value of equivalent diameter. And for the inner pipe, you have also the value of the diameter which you have used in the previous slide. And the mass velocity, which you have calculated in the fifth step, right? And the last step is the viscosity. You have to calculate the viscosity of these two fluids. So viscosity is mainly a function of temperature. So viscosity of the fluids, usually the benzene and the petroleum fluids, usually decreases with the increase in temperature. So what you have to do is you have to get the value of the viscosity at the caloric temperatures or the average temperatures that you have mentioned in the initial or the first slide, right? So in order to get the value of the viscosity, what you have to do is, so this is the step number 6 for the annulus region, and this is the step number 6 which is determination of the viscosity for the inner pipe. So the sixth step, which is the determination of the Reynolds number, and before going into the determination of the Reynolds number, you have to calculate the viscosity. And the viscosity, at what temperature you have to calculate the viscosity? At the average temperature, right? So figure number 14 will be used to determine the viscosity of the toluene at 130 degree Fahrenheit. So let me just go to the next slide. So this is the figure number 14, right? So in order to determine the viscosities, right? So this is the viscosities on the right hand side, right? So the viscosities are given in the centipoise, and this is the temperature axis on the left hand side, and this is again the XY table, right? And the value of the X and Y, you have to calculate, or you have to get the value for the different liquid stream. So for example, you are given with the average temperature for the toluene, which is 130 degree Fahrenheit. So you have to select the initial point, which is 130 degree Fahrenheit, right? And the second step is you have to select a second point so that you can draw the straight line, and this straight line will intersect this viscosity axis, and you will get the value of the viscosity. So the question is, from where you can get, or you can put this point on this XY diagram. So in the appendix of your book, you can get the value of X and Y. So in the previous page of figure 14, so for the 14, so for the toluene, the X value is 13.7 and the Y value is 10.4, right? So X value is 13.7 and the Y value is 10.4. So after putting the single point over here, this will be your second point and this will be your starting point. That is the average temperature for the toluene, right? So start a straight line from here and pass the straight line from this point, and you will end up with the straight line up to this point, which is the value of 0.41, right? So on the upper side, the viscosity is increasing. This is 0.4. and my green line is intersecting at a point which is the value of 0.41. In order to convert the value of this centipoise, you have to multiply it with the 2.42, which is the conversion factor, and you will get the value of pound per feet per hour, right? So the viscosity of the toluene is 0.99 pound per feet hour, right? Similarly, for the benzene, the average temperature is 100 degree Fahrenheit, right? And similarly for the benzene, so you have to put the initial point, that is the 100 degree Fahrenheit, which is the average temperature, and you have to select the second point, which is in the XY diagram. To get the second point, you have to get the value of the X and Y for the benzene, which is again given over here. For the benzene, the XY value is 12.5 and 10.9. And after putting it over here, you will get the second point. And similarly, after drawing the straight line, you will get the value of the benzene, which will be equivalent to 0.5 centipoise. In order to convert the centipoise into other units, so you will have to multiply it 2.42 and you will get 1.21 pound per feet hour, right? So by using figure number 14, so you have just received the values of the viscosities for the toluene, which is the hot fluid, and the viscosity of the benzene, which is the cold fluid. So the next step is to determine the Reynolds number, right? So the Reynolds number formula is given over here. For the annulus region, you have to use the equivalent diameter. The value of the equivalent diameter you have calculated in the previous slide, and the mass velocity, which is 767,000, which you have calculated over here, and divided by the viscosity. You will get the values of the Reynolds number for the annulus region, and on the similar ground you will get the values of the Reynolds number after putting the values for the Reynolds number for the inner pipe. So this is the diameter, right? And this is the mass velocity divided by its viscosity that you have calculated from the figure number 14, and you got the value of the Reynolds number for the inner pipe, that is 89,500. So after completing the sixth step, the seventh step is to determine the Colburn factor, which is the JH factor. And the JH factor could be calculated from the graph or the figure number 424, which is given in the appendix, and I will show you in the upcoming slide. So what you must have the value of the Reynolds number in order to get the value for the JH factor for the annulus side as well as for the tube side, right, or for the inner pipe side. So this is the graph, right? So let me just so this is the value for the Reynolds number right, which is given over here, the Reynolds number value for the annulus region is 59,000, right? So this is up to some value, this is the nearest value of the 59,000. You have to draw the vertical line until it will intersect this line, right? This is, which is in the turbulent region, and then you will draw the horizontal line and you will get the value of the JH, right? The value of the JH for the annulus region, which is, you know, in between 100 and 20. If you zoom that value, you will get the value of 167, right? And similarly, for the inner pipe, the value of the JH would be calculated from the Reynolds number. The Reynolds number is 89,500. So this is 89,500, and ultimately you will draw the vertical line until it intersects this diagonal line, and then you will draw the horizontal line. You will get the value of the JH, which is in between the 200 and the 300. If you zoom this graph, you will get the value of the JH for the inner pipe, that will be equal to 236, right? And the eighth step is to determine the value of this specific heat. So I believe the values are also calculated in the first step, in which we had performed the heat balance, and we have to use the values of the C for the specific heat for the hot fluid as well as the cold fluid. So the eighth step is to determine the specific heat and the viscosity and the thermal conductivity, right, at the caloric temperatures, right, or the average temperatures, whatever you have selected initially, and to compute this parameter, right? So in this parameter you have specific heat, viscosity and thermal conductivity, and what you have calculated so far, you have the value of specific heat so far, right? So you have the value of the specific heat so far that you have calculated in the first step of the design of the double pipe heat exchanger. You have calculated the value of the viscosity. Now the third step is you have to calculate the value of the thermal conductivity for both the fluids, which is toluene in the annulus region and the benzene in the inner pipe. So to get the value of the thermal conductivity at 130 degree Fahrenheit, right, so you have to go for the table number 4. So the thermal conductivity for the toluene, which will be equal to 0.058 at 130 degree Fahrenheit, and for the benzene, which is in the inner pipe, the thermal conductivity is 0.091 BTU per pound per hour per feet square, right? And you can get the value of the thermal conductivity from table number 4 at the temperature of 100 degree Fahrenheit. Let me just show you, right? This is the table number 4. I have selected the particular rows, that is for the benzene and the toluene, from the table number 4 in your book. So the values for the thermal conductivity of the benzene is not given exactly at 130 degree Fahrenheit, and similarly the value of the benzene is not given at 100 degree Fahrenheit, and value of the thermal conductivity is not given at 130 degree Fahrenheit. You can just simply interpolate the value of the thermal conductivity, right? So for the given temperatures, let's say the average temperature is 130, right? So you are given with the range from 86 to 167, and you are given the 130, which is in between this value 86 to 167. So you are given the in between value, right? So this will be the formula that you can use, the interpolation formula. So you can use any the interpolation formula from the internet. You just put the values and you will get the value of the thermal conductivity exactly at 130 degree Fahrenheit, which will be in between this value, right? So as you can see that the difference is not so much, so you can use the average value of these two, right? Thermal conductivity's value. So So in this way, you can have the value of thermal conductivity for the toluene, which is the hot fluid in the annulus region, and you can get the value of the thermal conductivity for the cold fluid, which is benzene in the inner pipe. And then you have to compute this parameter, and which you will use in the Coleman factor to determine the film coefficient. So after putting all the values of the specific heat and viscosity and thermal conductivity for the annulus region as well as for the inner pipe, you will get this value, that is 1.78 for the inner pipe. So the step number 9 is to determine the film coefficient for the annulus side as well as for the tube side, right, or for the inner tube side. So the shell side or the annulus side film coefficient is H0, which is basically obtained after rearranging this equation. All right, let me just show you the other equation. That this is the equation, right, the main equation. So from this equation we will just rearrange this equation, and we will keep the film coefficient on one hand side and taking all the other parameters on the right hand side, so that we can get the value of the film coefficient for the annulus side as well as for the inner tube side. So this is the formula that you will get after rearranging the formula. So this is the film coefficient for the tube side, and this is the film coefficient for the annulus side, sorry, and this is for the tube side. So this is the viscosity correction parameter, and the viscosity at the wall is not much high, so you can simply take this ratio is equal to 1. So we are putting this viscosity of the fluid at the viscosity at the wall, and this ratio we are putting the value equal to 1, right? And remaining all the other parameters, right, the JH parameter for the annulus side, the thermal conductivity, the equivalent diameter, and this ratio, we have all the other parameters, and after putting that in this formula, all the parameters, you will get the film coefficient for the shell side, that is 323, as well as the film coefficient for the tube side, right? And after putting all the values in this equation, and after the 9th step, the next step is the correction of the inner film coefficient, right? So when we determine the HI, so we are actually using the inner pipe inner surface area. So for the heat transfer, the rate of heat transfer formula, which is Q dot is equal to UA as delta T, the A as in that formula is the outer surface area of the inner pipe. So I have already explained that you have to correct the value of the film coefficient. So this is the correction formula. So you have the value of the inner film coefficient HI, you have the inner diameter and the outer diameter, right, of the inner pipe. So after putting that, this is the corrected value for the film coefficient for the inner pipe, right? So in this film coefficient, we are actually using the outer surface area or the outer diameter of the inner pipe in order to calculate this, the film coefficient. So after the 10th step, the 11th step is to determine the overall clean overall coefficient, that is represented by C, right? So this is the formula HI naught that you have calculated in the previous slide, H naught that is also calculated in the previous slide, and after putting all the values, you will get the value of the clean overall coefficient, the heat transfer coefficient, that is 149. So this is the overall heat transfer coefficient when the heat transfer or the heat exchanger is new. There is no dirt on the inner and the outer surfaces of the pipes, right? So this is known as the clean overall heat transfer coefficient. And after that, so you have to determine the design overall heat transfer coefficient. So in the design overall heat transfer coefficient, in order to compute the value of UD, which is the step number 12. So design overall coefficient, the formula is 1 over UD, that you have to calculate the UD, and the UC that you have calculated the previous slide for the clean overall coefficient, and you have to add the dirt factor, which is the resistance in the heat exchanger. So the dirt factor value is given in the question statement, that was 0.001, right? So we have the two fluids, right? For the inner fluid that is 0.001, and for the outer fluid, so we have two fluids, so we will multiply the dirt factor with the 2, right? For the inner side as well as for the outer side or the annulus region. So for the dirt factor, we will multiply it 0.001 with the 2, you will get the value of 0.002, right? So the dirt factor would be RD 0.002, and after putting the value, you will get, and after simplifying that, you will get the design overall heat transfer coefficient, which will be equal to 115 BTU per hour per feet square per degree Fahrenheit. So this is the summary, right? So the clean overall coefficient is overall 149, right? So when you add the dirt factor, the design overall heat transfer coefficient is 115. For the inner pipe, that is 276. For the outer pipe, that is, for the annulus region, that is 323. This is overall summary of the heat transfer coefficients. So after completing the 12th step of the design overall heat transfer coefficient, the next step is to compute the surface area by using this formula, that is the heat transfer rate is equal to the design overall heat transfer coefficient multiplied by the surface area multiplied by the delta T, which is the temperature difference or the LMTD. So which may be translated into the linear length. So after calculating the area of the overall heat exchanger, you have to convert this area into the linear length of the double pipe heat exchanger. So I will show you how to convert this area into the linear length. So if the linear length should not correspond to an integral number of the hairpins, so the integral number of the hairpins must be 1, 2, 3, 4, right? So this is the integral number. So a change in the dirt factor will ultimately result in the integral number of the hairpins. So if you are getting the linear length which corresponds to 3.5 or 4.5 of the hairpin, so you cannot use 3 complete hairpins and half hairpin. So this is not the right way. So you have to use either 1, 2, 3, 4 or 5 hairpins in the design of the heat exchanger. So once you change the dirt factor, you will ultimately get the integral number of the hairpins. The recalculated dirt factor should be equal or exceed the required dirt factor by using the next larger integral numbers of the hairpin. I will show you. So this is the formula, the famous formula from which you can get the surface area. So keeping the surface area on one hand side and remaining all the other parameter on the right hand side, you will get overall surface area is 50.5 feet square, right? This is very simple step. So the next step is you have to calculate the linear length from this surface area, linear length in feet. So from table 11, and for the IPS standards of the inner pipe, which is given here 1 into 1/4 inch, the standard pipe. So this is the external surface area per unit linear length, right? This is 0.435 feet square per feet, right? So let me just show you in the table number 11. So this is table number 11. I have just taken the row which is relevant to our interest. So this is the nominal pipe size, IPS standard in the inches, 1 into 1/4. So the surface area per unit linear feet, the units are feet square per unit linear feet for the outside pipe, that is 0.435. So what you will do is, so you will divide the calculated surface area that you have calculated in the previous slide divided by the external surface area per unit feet. So the feet square from here and the feet square over here will be cancelled out, and there will be a feet square over here, and ultimately it will be translated into the linear fit. So the required length, so how can you calculate the required length? By dividing the surface area divided by the external surface area per unit linear length. So after that you will get the value that is equal to 116 linear fit, right? 116 linear fit. What does it mean? So the linear fit is, let me just bring my pen over here. So the linear fit is 116. It means this is the linear length from this point to this point. This is 116 feet. This is the actual length, right? So in the question statement, you are given with the 20 feet length hairpin, right? For example, this is a hairpin, right? So its length is from here to here is 20 feet, right? From 20 feet, right? When you open this length, right? When you open this hairpin into a straight line, right? Into a straight line, this 20 feet hairpin will ultimately result in 40 feet linear length, right? It means that the linear length or the effective length of a single hairpin of 20 feet would be 40 feet, right? How? So this is the overall length of a single hairpin. When you open it into a linear length, so it will be into 40 feet, right? So what you are getting the linear length of the heat exchanger is 116 linear feet. So what you have a single hairpin of 40 feet linear length. So in order to reach over here, you will multiply 40 with 3, you will get 120. It means that in order to design that particular heat exchanger, you will be required 3 hairpins in series, right? So you required a 3 hairpins similar to like this one, right? In order to fulfill the required criteria, right? So nearest number of 116 is 120, right? 120. So the single hairpin has a linear length is 40. When you divide it over 40, so 40 on 43, and you will get the number 3. So you can simply say that you have required 3 20-foot hairpins in series in order to meet this criteria of the 116 linear fit of the heat exchanger. So the next is you have to recalculate the surface area. So you have the surface area of 116 linear feet length, right? So what you have to use is you have to use 3 20-foot hairpins, which will have 120 linear feet length. So you have to calculate the surface area once again. So how you can calculate the surface area once again? So similarly, you have 120 feet linear length, right? You will multiply it with this area. You will get the actual surface area, that is 52.2 feet square. Previously, you had the surface area 50.5, but after getting the value of the total number of hairpins from here, that is 3, you have just calculated the required surface area, or would be 52.2. From this surface area, you have to calculate the dirt factor will be accordingly. For the dirt factor, you have to redesign the design overall heat transfer coefficient with the actual surface area. Previously, you had calculated this UD value from the design overall heat transfer coefficient, right? So this is the corrected value of the design overall heat transfer coefficient based on this surface area, and similarly you have calculated the dirt factor based on the new design overall heat transfer coefficient. So the new value is 0.0023. Previously this value was 0.0022, right? So the last step of this design problem is to determine the pressure drop in the annulus side or as well as for the inner tube side, right? So the left hand side we have to determine the pressure drop in the annulus side, and from the right hand side we determine the pressure drop in the inner tube, right? So for the annulus side, you have to determine first of all the Reynolds number, right? The Reynolds number for the annulus side and the Reynolds number for the inner tube, right? So there is one most important thing is that the formula of Reynolds number is same, but the equivalent diameter for the pressure drop calculation is different, right? So I have already explained this one in the previous lecture. So you have to use this equivalent diameter in order to get the value of the Reynolds number when you are going to perform the calculations for the pressure drop, right? So this is the value of the Reynolds number for the annulus side. So after putting all the values, this is the equivalent diameter, the mass velocity and the viscosity. You will get the Reynolds number value for the annulus side, that is 26,800, and the Reynolds number for the inner pipe, that is equivalent to 89,500, and you have already calculated in the previous slides. The next is you have to calculate the friction factor, right, and which is F. So the friction factor can be calculated after putting the values of the Reynolds number for the annulus region as well as for the inner pipe. So this is the friction factor for the inner pipe and this is the friction factor for the annulus region. So what other parameters that you need is the specific gravity, which is given, and the density that for the fluid which is in the annulus side, you can get it from the table number 6, as well as the density for the fluid which is in the inner pipe. So you can just multiply the specific gravity. This is the correction parameter in order to get the value for the density. So the next step is you have the famous equation for the determination of the pressure. So this is the Fanning equation. So the equations are almost same, but there is a small difference that the equivalent diameter is used in the design or in the calculations of the pressure drop. For the annulus side, here the simple diameter is being used. So after putting all the values, you have Fanning friction, you have friction factor, you have the mass velocity, you have the length and the linear length of the hairpins, you have the gravity value, you have the density value, you have the equivalent diameter, and ultimately you will get the pressures in the feet, and after that you have to convert it into the PSI. So let's just first see that how we can convert this the pressure into the PSI by multiplying its density divided by this correction or the conversion factor. You will get the value of the pressure drop for the tube side, that is 3.2 psi, and the allowable limit is 10 psi. So if the calculated pressure is less than the allowable limit, so our calculations are correct. So if this pressure, which is 3.2, is higher than the 10 psi value, then you have to change some parameters, right, the dirt factor and other parameters to reduce this value less than 10. So the allowable limit is 10 psi. This is the maximum allowable limit. So you have to design your heat exchanger below this limit. So this is the pressure drop for the annulus side, and for the fluids which is entering and exiting the annulus region, so there are some entrance effects as well. For the entrance effects you have to calculate the pressure drops as well. So this is the formula to calculate the entrance effects. So for that you have to calculate the velocity into feet per second. So you have the mass velocity, you will divide it by 3600 multiplied by its density value. So you will get the velocity of the fluid in the annulus region, that is 3.92 feet per second. and the pressure drop due to the entrance effects, you will have to use this formula, and after that you will get the value that is 0.7. So previously you have calculated the pressure drop 23.5, here you have 0.7. You will add both the pressure drops and multiply by its density divided by its conversion factor. You will get the pressure in the annulus region, that is 9.2, and which is again the correct value or the less value of the allowable limit. The allowable pressure drop is 10 psi. You are in the range, so your calculated value is less than the allowable limit, so it means that your calculations are correct. So if this pressure 9.2, if this pressure is higher than this 10 value, so you have to change some parameters, direct factors and other parameters, so in order to reduce the pressure drop within the allowable limit. With this is the end of the lecture.